Okay, so we're going to talk about electrical principles, which is sub-element 5, and learn about current and voltage and resistance and those kind of things. A lot of this stuff, the terminology, was really determined by Benjamin Franklin. Although he never really actually discovered electricity, he did or is responsible for defining a lot of things that we use today, even though they're not exactly correct. But it was an arbitrary decision. The main thing is he determined that current flowed, what they thought was current, from a positive to a negative potential. He had a 50-50 chance. But they knew about atoms, but they didn't really know about electrons in his day. So we call that conventional current flow. Later on, they started calling things electron flow when you got into semiconductors, because the conventional current flow didn't exactly work in that model. So you have to look at how electrons flow, and also even in vacuum tubes, it's electron flow through the tubes. There's two basic definitions. We have direct current and alternating current. If it's direct current, whether you're talking about conventional or electron flow, it always flows in the same direction, from positive to negative. If it's called alternating current, then it changes direction from positive to negative. And it has to actually change polarity to be alternating current. If it's direct current, it can vary from 10 volts down to 0 volts and back to 10 volts. That's still direct current, because it never crossed 0 and changed polarity. Some of the terms, the basic fundamental thing is the elementary charge, and which is the amount of charge on a proton or an electron. They're both the same. And we measure that in coulombs, and how they came up with the fact that there's 6.24 times 10 to the 18th charges in it. I'm not sure, but that's the definition. When we talk about current, we're talking about movement of charge or movement of electrons, although electrons don't really move like that, but they can transfer charge. So they're a charge carrier. And we measure the charge in amperes and coulombs per second. So 1 coulomb per second is 1 ampere, named after the French scientist something Ampere. In fact, all of these things we're going to talk about were named after some scientist, long dead. We also have voltage, which is the potential difference between 2 points, and that creates a force we call electromotive force that can create the current flow. That provides the energy on the electrons to cause them to actually move and carry a charge from one atom to another.
So the motive is the moving of the electrons?
So the what?
The motive is the moving of the electrons?
The moving of the electrons moves the charges, but the electrons, turns out, electron moves at 0.01 millimeters per second. They don't move at the speed of light.
Charge moves at the speed. Yeah.
but charge can move at the speed of light.
Ooh, you've been reading more than I have.
Well, if you think of, take a tube, fill it full of ping pong balls, so they're touching one another, tap one end, one flies out the other end instantaneously, right? But they didn't move. The electrons or ping pong ball didn't move, but that energy moved from one end to the other. It's the same principle. Because the electrons get free from an atom, they move around until they recombine with another atom. And there's a force pulling them, which kind of tends to migrate the charges in that direction, but the electrons may just circle around and never really
But
get anywhere.
Isn't that like the 99.9998% empty space and those electrons are bumping each other? With all that
I don't know what the
space?
space is, but that's not on the test. Okay, some other terms, resistance, okay, which is the opposition to current flow. Okay, so we have voltage, which is trying to create current flow, is the force to generate it. Resistance is the opposition to it. Just like everything, there's a pro and a con. And we talked about direct current and alternating current. Your batteries all generate direct current. Yeah, your AC wiring in your house is alternating current. If it comes from a generator, like in your car, it's alternating current that gets converted back to direct current to charge the battery. Okay, some other terms are conductors, and that's basically the material that we use to connect components to allow current to flow. We typically use a metal. Copper is the most common. Silver is actually the best conductor. Copper is not far behind. We use gold in some cases because it doesn't tarnish. So a lot of times connectors will be gold plated so they don't oxidize. Sometimes aluminum is used, like if it's a chassis or ground connection, or antennas tend to be made out of aluminum. Sometimes copper, if it's a J-pole made out of copper pipe. But normally it's going to be either aluminum tubing or a copper wire when you make an antenna. And metals are unique in that as conductors, these are all materials that have atoms that have 1 to 3 valence electrons. I don't know if you remember your high school physics or chemistry.
Physics?
Well, it's probably more chemistry.
I just
Where you
made
come-
it through general math. What are we talking?
Well, electrons, or excuse me, atoms have different numbers of electrons. They equal the number of protons in the nucleus, so they're balanced. So protons have a positive charge, electrons have a negative charge. So if you've got an atom that's got 4 protons, it'll have 4 electrons. In the case of copper, forgot what it is. 30? I don't know. It's on a chart later. And I can't explain, but there's a like a protocol of, as you increase the number of electrons, how many electrons you have in each energy shell circulating the nucleus. And it goes up in an odd configuration. When you get to the topmost shell, regardless of how many electrons there are, that's the outer shell of that atom. And those electrons are the farthest distance from the nucleus, And they're the actually easiest ones to energize and actually leave the atom. And we call that the valence shell. Exactly where that valence came from, I'm not sure. But in the case of these metals or conductors,
I think it's some old dead guy.
oh yeah, named valence.
Yeah.
The valence energy level and the conduction energy band energy level actually overlap. So you can have, depending on the temperature of the atom, you can have free electrons escaping the atom into the conduction band and then recombining. And as you add heat, you get more of that effect. And when they recombine, they give off that extra energy back, which may be converted into heat, or depending on the quantity of it, into light. That's why on stuff that's very, very hot, when you see that combination, you see the actually emitting light, different colors, like in lightning. When you have enough potential difference that ionizes the oxygen and nitrogen, and then at some point those electrons recombine, and when they recombine, they're giving off all that energy, and that's where you see the flash, where the light comes from on the recombination.
So does germanium come from Germany and
Yep,
gallium from Gallipoli?
from Galilee.
Oh, Galilee.
Should be familiar with that one. Okay, we also have semiconductors, which are kind of in the middle. It's kind of a special case, and we can manipulate semiconductors a little bit and control current flow through them. Whereas we have insulators, we're just the opposite of conductors, and they essentially oppose current flow. They have 4 electrons in the valence band, and they're very, very hard, they're tightly bound, very, very hard to remove from the atom. There was a thing one of the previous students sent on showing the relationship between volts and amps and ohms. So when we talk about voltage or electromotive force, and that's why we use E to represent the force in the equations. In physics, they actually use a small epsilon, which looks kind of like an E. And that's the electric potential that exists between 2 charges, positive and negative potentials. So if I have a voltage E, which equates to a force, it can cause a current I, and we I to represent current. Exactly why we chose I instead of C, I don't know. But that's just the way it is. And that current will flow through some resistance R. And in this simple circuit, this is showing a battery which has a potential or electromotive force of so many volts, measured in volts, trying to force current through that resistance, which is opposing it. And the amount of current going through there and back to the battery, we measure that in amperes and represent it with an I.
I think Mr. Celsius claims C first.
Possibly,
That might be.
yeah. Because it wasn't because we use it for capacitance, because that came later.
Yeah.
This little water analogy showing, the height of the water in the tank equates to the pressure equivalent to the electromotive force. And if you and then we have a very high resistance here. The valve is closed. When we open the valve, we get current flow or water flow, still at the same pressure. This is just showing that potential difference we talked about between two conductors creates an electric field. And that's the actual force that we're talking about, the electromagnetic, electromotive force. And that's equal to the voltage divided by the distance between those conductors. So as you see, as the distance gets smaller, the force is going to be greater. So you have more energy density or force the closer those conductors get together with a given potential. We'll see that when we talk about capacitors. As you separate those things, that the potential is the same. It's still 10 volts between here and here, but the farther they are apart, the weaker that field is between them. And that force that we talked about, that is providing enough energy to cause an electron. To move from the valence shell outside and become what we call a free electron, has to provide enough energy for that to happen. Once that electron recombines with another atom, possibly the same atom, but in order to do that, it has to give off that excess energy, because when it's recombined, it's back to the same energy level that it was in that shell. The amount of that energy that it gives off determines the frequency of the waveform. We call those phonons. So if it's a very small amount of energy, that can give off very low level vibrations. As the energy goes up, you get into the radio wave spectrum. You get up higher, it gets into visible light. Even more, you get up into X-rays. So depending on that energy level, it will emit something in that spectrum, depending in that frequency, depending on the amount of energy. When we talked about the copper, it only has one valence electron. It has a total of 29, and they're always distributed like 2 is 8, I think it's 18, yeah, 2, 8, 18, and then in this case it's the last shell. If it had a couple more shells, it was a bigger atom, it would have a different number and finally wind up with some number between 1 and, I think it has to be between 1 and 8 in the valence shell. So if it's got a small number, it tends to be a conductor. If it's got a large number in the outer shell, it's an insulator. If it's in the middle, like 4, it tends to be a semiconductor.
That seems to be counterintuitive.
A lot of things are.
Oh, yeah.
And we talked about the different energy levels, and there's this thing called the Fermi level, which is another one of those physicists that determine. And in the case of a metal or a conductor, you can see that that red area overlaps with the blue area, which is the conduction band. And that's the energy level required for those electrons to be moving around. When it's in the red, it's still within the atom. It's the valence energy. Because they overlap, some of those electrons I think the way he defined that Fermi level is like there's a 50-50 chance that electron is either in the conduction band or in the valence band in a metal. When you get to a semiconductor, you have a band gap. So it takes energy in order to get it from the red to the blue. When you get to an insulator, you can see it's a much larger band gap, so it takes a lot more energy to cause that to actually conduct a current. And usually that's kind of catastrophic on an insulator when it does break down.
So we're
There's usually
talking,
smoke and flames and things.
so we're talking about bands and not symphonies or orchestras.
Yes. Jazz bands. So the first question is, what's the electrical term for the force that causes electron flow?
I always get that one wrong, Dan. How about you?
Probably D, wouldn't it?
No, it says
Oh,
a
did we
force.
talk about inductance?
It's a force. That like Luke Skywalker and
Be the current is the flow itself.
I don't see any current up there.
Or
Yeah, they use the term electron flow, but yeah, substitute current. What's the force that causes current to flow?
the force that causes it would be able to.
Right.
I always get that one.
Because they, the force is the electromotive force. We measure it in voltage and we tend to talk about it. We say voltage instead of electromotive force. So I didn't word the question. Maybe it was done that way on purpose to see whether you understood the difference. So when we talk about current, okay, they always define it as the flow of electrons. I define it as the flow of charge. Because you'll see when we talk about alternating current, the electrons are going back and forth. They don't really go around. So how could that work? But the charge is moving and releasing energy. And that's how the energy actually gets from one point to another, whether it's AC or DC. When we talk about conventional current, remember it's positive goes to negative. We measure current in amperes, and we use A to stand for amperes, a capital A. And it's defined as 1 coulomb per second. So it's like 6.54 10 to the 18th charges per second to make up an ampere.
So what does a coulomb look like when it's moving?
A bunch of charges. Now, I don't know what a charge looks like. It's a fuzzy thing. I have to look into that someday. I've never seen them define a charge per se. We talk about them. But
In Civil War, Revolution, these
Yeah.
are what charge was.
Right.
And even World War One, what charge was.
I think it's kind of a way talking about the amount of energy that's energizing the electron and then coming in and being released.
Fix bayonets and go forward.
There's another one of these water analogies where the height is the voltage. The amount of flow through the pipe is equivalent to the current or the amperage. And the resistance is how much resistance there is in that pipe, which reduces the amount of flow or the amount of current. So the water analogy works for probably 80%, but
DC.
yeah, for DC.
Not going back up.
What is the name for the flow of electrons in an electric circuit?
I don't know that. You know that one, Jack?
That's gonna be A or B.
What was the electron? What's that river in that?
Remember where they call it flow of electrons, I call it flow of charge. Okay. And what is charge? Coulombs. Coulombs per second is what?
Fuzzy things?
I don't know.
Remember an ampere was 1 coulomb per second?
So Dakota, what do you think? E current? Hmm.
Oh, just to get you in practice, use the phonetic alphabet. Alpha, Bravo,
Doggy.
Charlie, Delta, because you'll have to learn that later on.
Delta.
I'd go with Delta current.
It's a flow. Flow, mighty river. Flow.
Okay, electrical current is measured in which of the following units?
Amps.
Doggy.
Delta. Alright. Okay, we're talking about resistance, which is the opposition to current flow, whether it's DC or AC, I threw RF in because there's a question that relates to that. And RF is just alternating current. It's not really any different, but a lot of times we talk about RF, but it's just alternating current at usually a higher frequency. We measure resistance in ohms. Again, one of those old German scientists. And we use the Greek letter omega, which is that little horseshoe looking thing, to represent ohms.
How does a fat person find to go with their pants?
Okay. Or just bending over. There's another one of these analogies with the constriction like we saw before. So what are the units of electrical resistance?
The ohms.
Ohms. Charlie,
Yeah,
what type of current flow is opposed by resistance?
Be all of them.
All right.
You know, I
Uh,
used to do AC work. Which was a long time ago.
Okay, so we talked about direct current. Because it never changes direction. That's why we call it direct current. And that's what you're going to get out of a battery or a DC power supply. That's the most common sources.
so how many elephants did Edison electrocute in his demonstrations?
I heard it was a few, I don't know, but there weren't as many animal rights people back then, so they didn't put him in jail.
Did they take the carcass to the local homeless shelter and feed the homeless?
I don't know, probably not. Okay, so your typical household voltage is 120 volts AC. And it's a sinusoidal waveform. And most of your basic alternating current waveforms are a sinusoid. It may be a combination of sinusoids at different frequencies, which creates a different looking waveform, and we'll talk about that a little bit later on how they can combine. But the basic thing is it has to alternate between positive and negative directions. So it has to change direction to be alternating current. That's where alternating comes from. This just shows how the sine wave is actually generated. If you remember any trigonometry, where the sine is the opposite side of the triangle, into the hypotenuse. So if we look at this circle and we have these radials at 30 degrees, the sine for each one of those is going to be the height from this base up to there. And you see that's mapped over here to this graph as we rotate. And that's actually how you generate a sine wave, by rotating those radials around and plotting what the sine value is. Why it's called a sine wave. There's a formula there for all that, but you don't really need to know that until the general.
Thought that was manga.
Which of the following describes alternating current?
See,
Yeah, I like that.
Everybody with Charlie?
Charlie, yep.
Okay. Because it alternates, it has a frequency. And the frequency is how many times it alternates per second. That's how we measure it in the time domain and do it in seconds. And we measure that in hertz, another one of these old Germans. I think it was Heinrich, wasn't it?
I think you're right.
Because it's a capital name, okay, it's represented as capital H, little z. It's important, it's a test question. The period is going to be the reciprocal of the frequency. In other words, how long it takes to change polarity, the amount of time. So if you divide the frequency into one, okay, you're going to get the period, or vice versa. One divided by the period is going to give you the frequency.
So you got to have the whole wave to measure it, right?
The frequency is one complete cycle,
Right.
like this period here, that's one cycle.
Cause I know they talk about half wave, so if we talking half wave, we're just talking about right there, yeah.
Right.
Okay.
Right. And most of your antennas will be resonant at a half wave. So you'll see a voltage or a current waveform like this on the antenna. You'll see a voltage waveform from here
Bottom cross.
to there.
90 degrees out of phase.
Because the
You
end
might
of the
even
end of the wire conducts no current and has a very high resistance, therefore it has a high voltage. What describes the number of times per second that an
See?
alternating current makes a complete cycle?
You see? Either wavelength.
Number of times per second, not the number of seconds.
Number
You were jumping ahead.
Oh, no, per second, but the alternating.
Yeah.
It's the frequency. How often it changes.
How frequent?
Well, that makes
Yeah.
a frequency then.
Right.
Yeah.
What's the unit of frequency?
Hertz.
Hertz.
Alpha.
Okay. So we talked a little bit about conductors. There's some little animations here showing a conductor. We can have electrons running around because of that overlap of the valence and conduction energy bands. And that will be proportional to the temperature. When we apply a voltage, a potential across that conductor, you're going to apply more energy and create more free electrons, and you'll tend to have the charges move in the opposite direction.
So if the electron flow is temperature related. Okay,
Can be, and that's part of it.
all right. So you would think that is that the temperature rose, and in physics, you have more electron flow,
Right.
but in practically, you get more resistance.
That's true. That's one of the things of metals, which we don't go into in the technician, but resistance goes up with temperature. Unlike-
But those electrons are moving.
It seems
Wouldn't
counterintuitive.
resistance cause heat?
Hmm?
Doesn't resistance cause heat?
Typically, because you're having electrons recombine and they're giving off energy, usually as heat.
Right.
Whereas in semiconductors, it's just the opposite. The resistance goes down,
So the electromotive.
which is why in solid state devices, you can have thermal runaway. Because as they heat up, they carry more current.
Which is why when you're at Smelly's bar, and your base is thumping and your voltage drops, your amps draw more current, and then your amp dies and the party ends.
Yeah, we've seen this before, just showing the single free electron in copper. And more on the, just another chart showing the conduction and the valence bands. The important thing there was the band gap, which will come up when we talk about solid state stuff. Most metals typically have very low resistance to current flow at room temperature. Keep Byron happy. They measure it normally at 20 degrees centigrade, and they come up with these numbers on the resistivity. And they use the little rho symbol, where it's the reciprocal of the conductance. Silver is, of the metals, the best conductor. And it's 1.59 times 10 to the minus 8. I know you notice there's $2 there because silver is relatively more expensive than copper. Although today, copper isn't cheap either. But that's the reason we use copper most of the time instead of silver, because of the cost. And you notice there's not that much difference in the conductivity or resistivity. Whereas gold actually is quite a bit more resistive. And we don't use it except, like I said, on plating conductors or connectors, things like that, where you care about oxidation. Because both copper and silver oxidize, where gold won't, so it'll handle the environment much better.
There has to be a barrier between gold and copper, because they're not compatible.
Right.
So what they do when they gold plate contacts to protect them, you have to put a thin layer of, you electroplate a thin layer of silver first, and then you electroplate gold over the top of that. Because you need that barrier between them.
And you can see that aluminum is quite a bit worse. And then mercury, which sometimes you see as a conductor, if you ever looked inside of your older thermostat, which had a little mercury switch in there that conducts, or some of the mercury wetted relays used to use that, and that was actually the conductor.
Our mercury thermostat finally died after 55 years.
Only 55 years?
Yeah, you won't find too many of them with mercury in them anymore.
Over more, no.
Yeah. Thermometers either. Why are metals generally good conductors of electricity?
Rubber.
I have to say D on that.
D?
Mm.
Well,
one.
let's see.
Move protons around, you might see some interesting things.
In most cases, we don't have such a thing as a free proton. In order to get a proton out of an atom, you have to kind of put it in one of these high energy colliders, and
Yeah,
Yeah.
strong force.
they pretty much stay with the atom. But electrons can be easily, particularly in a metal, easily removed. And you create two ions. You have the atom itself is now a positive ion, and the electron is a negative ion. And sometimes they refer to them that way when we talk about semiconductors.
So at CERN, how much does it cost to free the protons?
A lot.
6.28 times 10^18 dollars.
Why are metals? Oh, we said. We talked a little about insulators. So you definitely need cases where you need to prevent conduction. So you can kind of control the flow. And we call these insulators. It might just be the insulated coating on a wire to keep it from making contact with other things. Standoffs, all kinds of enclosures, things like that, where you don't want them to be conductive. They're usually made out of some insulating material, typically plastic or glass. The resistivity of those materials is here, and you see that quartz is surprisingly the highest, which I never knew. Glass is what we typically use for an insulator material. Silicon, pure silicon can act as an insulator. If it has an impurity, it can act as a semiconductor. We'll talk about that in a little bit. There's also plastics, which are probably more common than using glass, but that's not a test question.
So you're talking about the silicon that's become a doper?
Uh-huh.
Okay.
Let's see. This just shows the comparison between conductors and insulators. And they threw this thing, and I had to go find out what that really meant. Is low electronegativity and high electronegativity. And basically, it's how tightly bound the electrons are to the atom. So the higher the electronegativity, and the name is very confusing, the harder it is to free that electron. Which of the following is a good electrical insulator of the following? Bravo. Okay, so we learned that current is measured in amps. It's 1 coulomb per second. And coulomb is a whole bunch of elementary charges. You don't have to remember that 6.24 number. Alternating current changes direction, polarity, per cycle. Electromotive force, we measure in volts, and that's the force that is causing current to flow, whether we talk about it being electron flow or charge flow. We measure frequency in hertz. It's the number of cycles per second. It used to be cycles per second when I was growing up. And then somebody decided to honor Mr. Hertz, and they changed it to hertz. Which is nice, but it's really cycles per second. It's less confusing.
Was that when his kids had the truck company and was able to buy that Honda?
Oh, maybe. I
Yeah,
wonder if they're relatives. We measure resistance in ohms. Sometimes we show it with a little omega sign. And it's the opposition to current flow. And it's opposition to all, whether it's direct current or alternating current. Pure resistance is not frequency dependent.
Resistance is resistance.
Resistance is resistance. As opposed to, we'll talk about impedance, where that's frequency dependent. So it acts as a opposition to current flow, but it varies depending on frequency. Conductors are basically metals that have many free electrons. They're 1 to 3 electrons in the valence shell, so they're very easy to free. Doesn't take much energy. And insulators have tightly bound electrons. So they have essentially a full valence shell. Why those two things make a difference, I don't understand the physics. And you don't need to know it either, but if you're interested, go look it up.
That's why you get different readings on different frequencies when you're measuring your power and your SWR. Correct?
Yes,